Hello. So far, we've talked about support vector machines and perceptrons and how we can use them to draw lines when the dataset is linearly separable. But what happens when the dataset is not linearly separable? What happens in this case? This is the exclusive OR classification problem. We have got zeros at 0, 0, and 1, 1, whereas we got the target label is 1 at these 2 points, right? But it's impossible for us to separate these points the way they're drawn right now very neatly into two different classes. We can do it using something else other than a line. Let's say we can use a circle that we can make, and then we can perhaps cut out this bit that is one part of the feature space that belongs to this X class, and then we have got another part of the feature space or what's left of it as everything belonging to the other class, right? But let's take a higher level look at what we've done so far when we were making these linear discriminants, just like this one. If you take a, and this is not the exclusive OR classification problem, this is simply the AND classification problem, as you can see. And what we can do is perhaps if we take a pair of scissors, then what we can go ahead and do is we can cut along the linear discriminant line. And as I've been telling you, classifiers are a way of partitioning the feature space into two different parts such that one group or one region belongs to one of the classes and the other one to the other one, right? So this is what we are going to do. So what we've done so far is we have partitioned this feature space into these two parts. That's what these classifiers do. Now, the problem we have with this data set, this linearly non-separable data set, the exclusive OR data set, is that we're not able to cut it, right? But can you figure out a way in which we can use this and we'll still be able to make a single cut in the feature space, which is a linear discriminant? So linear discriminants are only able to make a single straight cut in the feature space, right? That's why, because they're linear, right? And we've seen that this was a single straight cut in this feature space, and that's what we got, right? So it works in this case, but it may not work in other cases. So if we have this exclusive OR problem, it's impossible to make a single straight cut the way we see it right now, so that we end up with all the classes or the classes can be separated neatly. But what if we fold this space? Let's say we fold it along this line, right? So we fold it like this, right? Then as you can see, these both x's, and if you have a piece of paper in front of you or you're doing this experiment yourself, it would be much easier for you to understand. But if you have that, you can probably see that these 2 points, the two x's that we had, now essentially map up to the same region in the feature space. And now what I can do is use my selenite crystal again to determine the maximum margin line between what we see in this point. So there are these 2 points, and then there is this, right? And we can make a cut, right? So let me first use my selenite crystal to draw a line that separates these two classes, and then we're going to try to separate it. Okay, so I'm going to make a cut. Okay. Okay. So let's say we come up with this line, and now if we cut along this line with my scissors, then what I do is what we get is this. So remember, we're making a single straight cut, but we folded the paper, right? And what that means is we obtained this bit, which is the region of these O's, and then we have got two bits left over, which are these X's, right? But we've been able to separate the O's from the X's by making a single cut. Now, this idea of folding the space and then making a single straight cut is quite a fun thing. It's called the fold and cut theorem, and I'll be posting some resources that actually do a better job than I just did in explaining it. But in terms of machine learning, understanding this is important because we were limited in terms of one of the limitations of using any linear discriminant, be it a perceptron or be it a support vector machine, is that they're able to partition the space using a single straight cut. And that means we're not able to solve linearly inseparable classification problems. which we really want to do. You can solve those using other classifiers, for example, a nearest neighbor classifier, but using linear discriminants, you will not be able to do it. And there are some really nice properties that we haven't talked about of these linear discriminants that make them really attractive for us. First of all, they're simple, right? And it's a single straight cut in a feature space, and you are done. And then we have a very neat notion of the concept of margin in when we talk about linear discriminants, right? So we want to keep that when we are talking about classification, right? So there are some other neat properties that we're going to talk about in the rest of this module, but these two should be enough for now for you to like linear discriminants, right? So what we have in front of us is a way of using linear discriminants, single straight cuts in the feature space, to make linearly non-separable boundaries, right? So that's pretty neat, right? So you can welcome to try out with other data sets that are linearly non-separable, and I'm going to take an example of another data set that is not linearly separable, and then we are going to try to see if we can make a single straight cut that separates the two classes, right? Okay, so let me take another piece of paper. Let me draw some points on top of it. Okay, so there are going to be some X's, okay, and then there are going to be some O's. Just a sec. So this data set is not linearly separable, right? And I welcome you to pause the video and think of a strategy that you can use that to fold this piece of paper so that once you make a single straight cut in this feature space, you end up with two different parts, right? And it's really easy if you think about it a little bit. So what I'm going to do is I'm going to do some cheating, right? So I'm gonna draw some lines on here just to orient myself. What I've done is make a cross at the center, right? And then I'm going to fold along those lines. It's not necessary to draw a cross. I just wanted to do that so that you can see it in the camera. Okay. So what I'm going to do next is I'm going to fold it neatly in half along one of those lines, and then I'm going to do it along the other line, right? And I've done that, right? And as you can see, and this is my mapping from the original feature space that you see here onto this new feature space that you can see now. And if you take a look at this piece of paper from this side especially, you'll be able to see it better. You see that all the outer boundary ring points, those where the O's are now over here, whereas all the internal points are now clustered here. So if I make a cut along this, I should be able to separate these two. So to do that, first I'm going to draw a line, okay, and so I can cut along that line easier. Okay, so I've made a line, and I hope if I cut along this line, I should be able to separate the two. Okay, so let's do that. Okay, moment of truth. Let's see what we've done here. I hope it works, but even if it doesn't, you get the idea. This is it's quite neat actually. So we got this. This is the central part, and we see that with the folding and a single straight cut, what we managed to do is we have separated the two classes. And that's how we are going to be able to do nonlinear classifications using linear discriminants. And this idea is important to understand not only in the context of support vector machines, but in terms of other machine learning algorithms. In even neural networks and deep neural networks, because they do something similar, just use a different means to the same end. What we've done so far is all we had was a linear discriminant, so we could make a single straight cut in the feature space, and we wanted to use this strategy to be able to do classification when the classification problem was not linearly separable. So what we did then is we changed we folded the space in which these points or in which our data occurred, the feature space, right? So let's talk about that a little bit. What does folding actually mean, right? So let's say if we have this data set, right? This very simple data set. And if I fold this piece of paper, right? If I fold it like this, or if I make any fold in this in this space, let's take any fold in this space. Let's make a fold like this. Then what I've done essentially is I've changed the definition of distance between the points in different space. So these 2 points, for example, were much farther away before the fold than after the fold, right? You should be able to imagine that. Now these 2 points are much closer in this folded space in comparison to where they were originally. So if you think about folding, folding is nothing mathematically, it's nothing more than changing the definition of distance between 2 points in the feature space. So it's kind of like those sci-fi movies where we have a wormhole that warps the space. And if you get that warping in space, essentially you can go from one point in this space and time to another point in space and time. So you're able to do time and space travel, and it's pretty cool, right? And it's pretty much the same idea. That once we make a fold in this space, we introduce a fold in this space, we change the definition of distance. Points that were farther away in the unfolded space can become closer. And sometimes points that were closer, if we stretch the space between them or we transform that space, we can increase their distance. So folding is nothing more than changing the definition of distance, right? That's pretty cool because that means if I am able to change the definition of distance in the feature space in which my data points lie, I will be able to use that to make nonlinear classifiers, and I may be able to separate or generate more complex decision boundaries. And that's what we are going to do. However, before we go there, I want to give you an intuitive definition of distance, right? So we understand understand distance as we take 2 points and then we can calculate how these what's the distance between these 2 points. But we have a formula for that, the Euclidean distance, right? But if we change the definition of that distance, if we change that distance function, then we will be able to achieve a fold in that space. And then in that space, if I make a cut, we should be able to separate the 2 points. That's what we want to do. What we are going to talk about next in the lecture is going to build on this exercise. So I welcome you to try it out not only for the data sets that we have talked about, but for other data sets as well that are linearly separable. I'll be posting some challenge fold and cuts that you can make and you can try out and try to gain expertise in making these folds and cuts. So remember, the goal is again to use a single cut in the folded space to separate data points, right? And you can generate some pretty cool shapes with that. So please go ahead and practice that. So once we get back to our lectures, you'll be able to understand the underlying mathematics based on this intuition. Thank you very much.